morning, students. So, in the last class, we discussed about bending of cycles in curves. So, next we pass on to the moment of inertia. What is the moment of inertia? Is nothing but the expressions for the torque and angular momentum for the rigid body. That means the rigid bodies means which are considered as a bulk objects. We have come across this term already. That is summation of MI/RI square. This quantity is called moment of inertia, I of the bulk object. For a point mass mi at a distance of ri fixed axis, the moment of inertia is given as mi/ri square. So the moment of inertia for the point mass, we know that I is equal to mi/ri square. This considered for a bulk object means the moment of inertia for the bulk object is nothing but I is equal to summation of mi/ri square. In translation motion, the mass is a measure of measure of inertia. So in the same way for rotational motion also, the moment of inertia is a measure of rotational inertia. The unit of moment of inertia is kg meter square. Its dimension is ml square. So in general, mass is an invariable quantity of matter. That means except for the motion comparable of that light. But the moment of inertia of a body is not an invariable quantity. It depends not only on the mass of the body but also on the way the mass is distributed around the axis of the rotation. So to find the moment of inertia of a uniformly distributed mass, we have considered an infinitesimally small mass, that is dm. We are discussed in this dm in many cases before as a point mass and take its position r with respect to an axis. The moment of inertia of this point mass can now be written as di is equal to dm r square, because it's a very small mass that only we are taking as a dm. We get that moment of inertia of the entire bulk object. So we know that for entire bulk object means you have to take the integration. By integrating the above expression, I is equal to integral of di, that is equal to integral of dm r square. So we know that we have to give the integral for the dm. So that's why we are getting I is equal to integral of r square dm. So we can use the above expression for determining the moment of inertia of some of the common bulk objects of the interest like rod, ring, disc, sphere, etc. So this will be used for all these type of moment of inertia findings. We are using this expressions only. What expression? I is equal to integral of r square dm. Understood what is moment of inertia? Next we pass on to the next topic, that is moment of inertia of a uniform rod. So for uniform rod, we are going to find out the moment of inertia. So what are the things we are going to do for this one is, let us consider a uniform rod of the mass m. We are taking that as a capital M and length L as shown in the figure. I'll show you that. Let us find an expression for the moment of inertia of this rod about an axis that passes through the center of mass, and that is the perpendicular to the rod. So that should be given here very clearly. What are the things? The dx, that is a small area, and that is a dm for this area, that the mass is taken as in dm, and then the x is a distance and a minus l by 2, and this side is l by 2. Okay. First, an origin is to be fixed for the coordinate system so that it coincides with the center of the mass. Okay, and then the which is also the geometric center of the rod. So this is the center. So for this rod also, that is a geometric center, and that point we are taking as a center of mass coincidence, which is also the geometric center of the rod. The rod is now along the x-axis. We can take infinitesimally small mass dm at a distance of x from the origin O. The moment of inertia di of this dm, that is the mass, about the axis is, we know that the already expression here, just we are changing the distance r as a x. So we are replacing that r square as here x square. Same thing, other than that the remaining things are same. So that is di is equal to dm x square. So as the mass is uniformly distributed, the mass per unit length, we are taken that as a lambda of the rod is lambda is equal to mass by the length, that is a capital M by L. dm is a mass of the infinitesimally very small one, small length as dm. So that is, we are taken that x as dx. So lambda dx we are getting, dm is equal to lambda dx. So substituting the value of lambda here, lambda is nothing but capital M by L into dx. The moment of inertia of the entire rod can be found by integrating the di. So we know that what is I is equal to integral of di, that is equal to integral of dm x square, and we know that what is dm, and that is substituted again here, that is equal to integral of m by L dx into x square. So what are the constant values that will be taken out? That is that changing variables only we are going to integrate. That is m by L is constant one, and we are taking that as an outside. Then we will get that integral part as integral of x square dx. So I is equal to m by L integral of x square dx. As the mass is distributed on either side, what happened? So here now we are taking that limits, and that we know that one is a minus, other one is a plus limit, that is minus L by 2 as taken as a lower limit, and plus L by 2 as taken as a upper limit. So the constant is on the outside now. So I is equal to capital M by L integral of x square dx minus L by 2 as a lower limit, and plus L by 2 as a upper limit. And now we are after the integration, we know that what is x power n of dx is nothing but n x power n plus 1 by n plus 1. So what is here? Here the n is 2. So what is a thing we are getting here means my m by L into x cube. X cube is nothing but, how you are getting the x cube? You know integral, I know that. Or integral of xn equal to x n plus 1, x to the power of n plus 1 by n plus 1, that is the formula. Same thing for here also we are deriving. So x square means n plus 1 is nothing but x cube. In the denominator side also we are getting n plus 1, that is 3. So m by L into x power 3 by 3 minus L by 2 plus L by 2. Okay, dx is the integral of dx is nothing but the same. Okay, 1. And next we are substituting the value of L by 2. So placing the L by 2, what happened? L cube we are getting, in place of x we are going to substitute L by 2. Okay, in place of x we are substituting the L by 2 cube. So what you will get means L by 2 cube means, in the place of x, L by 2 means what? So L by 2 whole cube, you will get L cube by 8, right? And minus also same value. So already you are having in the denominator side as 3. So what you will get is L cube by 8 into 3 is 24. So L cube by 24 minus of L cube by 24, that is equal to m by L into minus of minus become plus. So that is L cube by 24 plus L cube by 24. So what you will get means we are taking the 2 L's, no? L plus L cube, that is 2 times we are getting. So I is equal to m by L, 2 times of L cube by 24. So 2 into 24 will get cancelled. You will get 1 by 12, and also L is outside, one L is there, and L cube, so L get cancelled, we will get mL square. So 1 by 12 mL square, that is our final equation. Understood? How will you get this? I is equal to 1 by 2 mL square. It is a very easy one. I'll repeat this one again, the integration part only. So first we are integrating the x square dx and taking the upper limit as minus L, upper limit as plus, and lower limit as minus L by 2, and after integrating you will get the x cube by 3 as the answer, and then we are going to substitute the limitation. So in the limit means you are going to substitute only in terms of x in replacing the x as a limit value. So in place of x you are substituting the L by 2, means L by 2 whole cube by 3 you will get. So that is L cube, and the 2 cube is 8, and already 3 is there, so 8 into 3 24. That this is for the first limit, that is upper limit. Now same you have to repeat for the lower limit also. The minus you will get, that is upper limit minus lower limit, so minus, and one more minus is there, you will put that minus also. Same thing you are also here also you are substituting in the place of x L by 2 the whole cube, so you will get L cube by again 8, and already 3 is there, so that is L cube by 24. So minus of minus becomes plus, so 2 times of L cube by 24, the 2 and 24 will get cancelled, you will get 1 by 12. And already you are having one denominator L, now L cube is there, so denominator numerator 3L, so 1L will get cancelled, you will get mL square, that is by 12, that is 1 by 12 into mL square, that is the I value. Understood how you are getting this value? So it's the easiest one, but you have to do it very clearly. Okay, now we will pass on to the problem that is related with the same moment of inertia of the uniform rod about an axis which is perpendicular to the rod touches any one end of the rod. So what is the solution is the concepts to form the integrand to find the moment of inertia could be borrowed from the earlier division. So what is the solution is the concepts to form the integrand to find the moment of inertia could be borrowed from the earlier derivation. Now the origin is fixed to the left end of the rod and the limits are to be taken from 0 to L. So here also we are taking it some origin, that is from the 0 to L as a limit, and we are taking that x as a distance, and dm is for the smallest distance. Same thing is repeated here, only the integral upper limits and lower limits are changed, that is there we are taken as minus L by 2 to plus L by 2. Here we are going to substitute as 0 to L. So same thing, mL x square, that is the limitation of the integral is 0 to L. Integral of x square dx, that is equal to m by L x cube by 3, 0 to L. So for in this case first we have substituted the upper limit, so you will get only one, that is L cube, and only one value, so no changes in the x cube also. So x cube in place of x we are just replacing as L, so you will get L by L cube by 3, and lower limit is 0, so you will get as same m by L. So here L denominator L is there and numerator L cube, so it will get cancelled, you will get L square. Say other the things has to be same, so I is equal to 1 by 3 mL square. Understood this one? It is very easy. In the uniform rod for the topic you will get the limitations as different. In this problem you are getting the limitations as 0 to L. Other than that everything will be the same integration values, and then the same thing. Okay, the integration part and everything has to be same, only the limitations as different, and it is very easy. And next we pass on to the next topic, that is rotational dynamics. The relations among the torque, angular acceleration, angular momentum, angular velocity and moment of inertia were seen. So in continuation to this, in this section we will learn the relations among the other dynamical quantities like work, kinetic energy in rotational motion of the rigid bodies. Finally, a comparison between the translational and the rotational quantities is made with the tabulation. So all these things we are going to see here. And the next is the effect of torque on the rigid body. That is the next topic. That rigid body has no non-zero external torque tau about the axis of rotation, could have an angular acceleration alpha about that axis. So the scalar relationship between the torque and angular acceleration is tau is equal to I alpha. Here I is the moment of inertia of the rigid body and torque is a torque in the rotational motion is equal to the force in the linear motion. So this is the torque on the rigid body. So what is the relation is tau is equal to I alpha, moment of inertia of the rigid body. Okay, the torque in rotational motion is equivalent to the force in the linear motion. This is the effect of torque on the rigid bodies.